Let me start. I'm actually going to start in the sitting position because this is a habit that I like to do. And it comes from, do we have any Russians? Yep. Russians in the room? In Russian, this is called posedieli. What I mean is it's a habit that you do before you make a journey. You sit down in Russia. And then you stand up and you go. So now, the second task is for you guys, and you're going to stand up with me on the count of 3. 1, 2, 3. Okay? You guys are n. Yeah? And I need you to do n plus 1, which is to go 1 row forward, please. Everybody. Come a little bit closer, 1 row closer. If you can. You can, obviously. You're already at the maximum. You can stay. You can stay at n. But everybody do n plus 1. Feel free to knock over the chairs or whatever you have to do. Just come a little bit closer because I'm going to need your brains. Okay, so we had Russian. My name is Ferak. I'm an Austrian programmer. And so for the Austrian part of you, how many Austrians do we have here? Okay, so more than half, actually. We're still on Austrian turf, let's say. So for the Austrians in the room, this will be kind of like a history lesson a little bit because we start actually in Vienna, in the 8th district of Vienna at the Kurt Gödel Institute for Logic, Mathematical Logic. And we will make a journey into my code editor. But for the non-Austrian part of this audience, this will be to show you that we have more than Arnold Schwarzenegger. Okay, so actually the idea for this talk started last week just here in the closure meetup. And I had a short example in JavaScript that we discussed, and they liked it. And so it's actually from our company. Christian is from my company, so he might know the guy that did this, okay. Let's say. But you can't tell him. But this is a disclaimer. I'm not going to talk about Elm and Reason, because those are functional languages for JavaScript. But I'm going to talk actually about the built-in, the out-of-the-box stuff for JavaScript and how to apply it functionally. And yes, of course, JS is everywhere now. So if you know Jeff Atwood, the coding horror blogger guy, he says that whatever can be written in JavaScript will be written in JavaScript eventually. Okay, and we continue our journey with Kaiser Franz Josef, very, very famous Austrian guy. He was primarily he was a Kaiser. We have an agile coach, right?
He just took off.
He took off, but I have a question for him. So what in terms of agile, or what, let's say, what in terms of Scrum was he? Was Kaiser Franz Josef?
Scrum Master?
No, he was the product owner, because he owned everything. If you didn't deliver on time, you would be like sent to Siberia or something. And of course, maybe he was also a computer, because before we had machines, a computer was actually a person. And yeah, let's get to the algorithm. The algorithm is a process or a set of rules to be followed by in calculations or other problem-solving operations, especially by the computer. And a computer can be a person, which it was for many, many years, because algorithms are very, very old. They actually come from about 3,000 years ago. From Euclid, he could already do them, and he was doing them, and they were doing them in person. Okay, but there's a problem with the algorithm. And it is that they knew how to do them, but they didn't know how to formally define them in mathematics. And then sometime came David Hilbert, a German mathematician. Does anybody remember him from math class, maybe? Do you have any buzzwords, let's say?
Awesome. Hilbert space.
Great. Yeah, okay. I don't even know that one. So he had lots of things.
Wasn't he the guy with the Hilbert's problems?
Yeah, you could say that. Yeah. He did have a problem, but it was called something else, actually. But he also had Hilbert's Hotel. Maybe you know that one. It's a bit kind of like what I did with M+1, actually. But Hilbert's Hotel is that you're the owner of the hotel, and you have n number of rooms, and n is infinite, so you have infinite number of rooms, and a guest comes to your reception. So what do? I forgot to say, every room is filled, of course. your hotel is full, right? So how do you get this person into a room? And there's a way to solve it, but it's not part of this talk, so I'm not going to talk about that. You can Google it afterwards. So he was actually a mathematician, basically just a mathematician, also a philosopher and a logician, kind of. And he was interested in the foundations of mathematics, which is axioms, which is called axioms, basically. And he posed the Entscheidungsproblem, which when I asked a colleague of ours, actually, Juliana, I asked her what she thinks is Entscheidungsproblem, and she said, this must be something in management. And I said, no, this is mathematics. So what is the Entscheidungsproblem? It is essentially what it's saying is that if, actually it's kind of a challenge for a definition of an algorithm, first of all. And what the Entscheidungsproblem is saying that if a statement in logic is true, then it must be provable. And if it is provable, then it must be true. Yeah? This is what he said, but the assumption that he was making is that logic is complete. So along came Kurt Gödel, our Viennese friend, and let me get the number right. He was 23 when he challenged David Hilbert's assumptions. He was very young, and he kind of showed the old guys how to do it. So what he did was he figured out a way how to write in logic, actually with arithmetic, so with numbers, this statement. This statement is not provable. He could write it down as a proof, let's say. So if I can prove it, I basically prove false, because it's a false statement. And you cannot prove false, it's impossible. At least I think. And if it is false, then, let me think about that. It's true, but it's not provable. So therefore he came up with the incompleteness theorems, which said that logic is not complete. It's in fact not complete. And so they needed another formal definition for the algorithm. And along came Alonzo Church. And around 1930, he defined the lambda calculus, which was the first use of the lambda character that I used in the beginning. And he was actually a professor at Princeton at the time. So he defined it, and he thought that this was it. This was the definition of an algorithm, yeah, a formal one that he could prove. But then Gödel came over to Princeton and visited this guy, and he looked at his proof, looked at his lambda calculus, and he said, "This is wrong. This is wrong. This is not true. It doesn't work." So Alonzo Church said, "Well, you come up with your own definition of an algorithm." And Gödel went back to Vienna, and he was in the States already at this time. He emigrated because of the war. And he defined recursive functions, where Church proved that this is equal to his lambda calculus. To which then Church told this to Gödel. He said, "Look at this. This is the same thing, man." And Gödel said, "Well, mine must be wrong then too." And along came Alan Turing, which hopefully everybody knows. And Alan Turing came up, of course, with the Turing machine, which he proved that is equal. He could prove it that is equal to the lambda calculus, and therefore also equal to Gödel's recursive functions. So all of a sudden, after 3,000 years, we had 3 independent proofs of a formal algorithm. And some philosophy, I don't know if there are philosophy students, but you might argue that mathematics could be invented or discovered. But if there are 3 equivalent definitions of something after so many years, then it might just be that it's evolving through time and you discover these things. Okay, and this is what it looks like. This was 1940 typed lambda calculus. And I cannot explain this to you. This is from a presentation by Philip Wadler, who will come later. But basically, I can explain you this one, which says that S is a function from A to B that takes A and returns B. This is type A. This is type A. This is type B. So S is a function that takes type A and returns type B. For example, takes an integer and returns a string. And S applied to T, so this function applied to this type will give you type B. Looks very, very familiar. You could say that this was actually the first programming language in the world, and this was basically 10 years before computers. Then this is kind of then a really fast forward, because lots of things happened afterwards, and functional programming only came in the 90s. So we jumped now from 1940 till this was, I think, in 70 or so, or 80. And Curry, Haskell Curry, was very important amongst other people, because he came up with, together with Howard, who was another mathematician, with the Curry-Howard isomorphism of or equivalence, which is the lambda calculus that I showed you applied to a program. So he proved that it could be, it's the same. It's the same. Basically, it's made functional programming possible. Right. So for me, this journey kind of started in 2012 when I saw a talk by Philip Waller, where he was the lambda man. And he kind of like wasn't on stage and just speaking, and then all of a sudden he ripped off his shirt and he had the lambda on his chest, which was pretty impressive. And he wrote, so first of all, he's kind of known as the father of Haskell, and not the Haskell Curry guy before, but the language, programming language. And he also wrote that theorems are for free, which is kind of an expansion on the Curry-Howard isomorphism. And he introduced, basically he introduced functional programming into the, let's say, more popular languages like Java. He did the generic types, which was kind of like the first functions. And so yeah, this is a thank you from him, from me personally, because he kind of set me on this journey. Okay, so this is the meat of this presentation. And it's actually quite easy to read. So R is a function that applied to a list of A will return a list of A for all A. So do we have any functional programmers here? Okay. Do you think you know a function that would satisfy this?
Map.
Map, identity function.
Okay. Identity is one, map is not one. We will get to that on the next slide.
Filter.
Filter is also not one, because you end up with only one A, not a list.
Well, no, like a filter might filter to like
A filter without a filter function.
Which is identity. So you could also make a map with identity function. But actually, there is a very simple one that is not trivial. So
sort.
Sort also requires a function because I need a comparer. So I'm looking for a function that doesn't need another function. So it touches the whole array, the whole list.
Slice.
No, because I get less. But kind of, yeah. Think of the sorting thing.
Reverse.
Yes, reverse. Reverse is this one. So, wait, let me get this. R stands for rearrangement, because all that's reverse does is flip the numbers, right? So if I do reverse on a list of A, I will get a list of A that is just reversed. If I do reverse on a list of B, I will get a list of B just reversed. So B can be a string, A can be an integer. If I map, I get a different type, at least in mathematics. And all of this stuff is provable. So you just kind of have to believe me because I just believe them. So okay, but no more theorems. You said reverse and sort if I apply a function. Map just goes this way. I think it's pretty clear now, yeah? Okay. And then I had find, which is kind of like filter, which goes from a list of A to A. So I find one thing. Or I can reduce where I get B, for example, a string out of integers. Okay, but let's get to reality, because this is really what enterprise code looks like. And this is the example that I was sort of got on where I found a bug. Well, I was trying to fix a bug actually, and then I used this refactoring example, let's say, in the closure meetup. So I was looking at this, and first of all, it was very hard to find the bug because it was very hard to understand what it really was saying. And I noticed a few things, like for example, that it's not reusable. I cannot really reuse any of these lines anyway. It's very hard to expand. If I want to like do something on each of these, then I have to actually adapt each of the lines. Yeah. I could apply a function or something like that to each of the lines or each of them. But it's just kind of, I call it the wrong type of BDD, bug-driven development. Because I know that he found this bug in production, for sure. And probably the undefined one as well, I would say. But it's not really his fault. I'm even less qualified to tell you about this stuff than the mathematics stuff. But in cognitive science, there are basically two types for problem solving, two cognitive styles. And I can't really explain it, but the thing that I got of it was that either you take an existing solution and you try to make it better as much as you can, or you find a new way to do it. Yeah? So you kind of think outside the box and you try to improve it by doing something new. And most of us, I'm not going to make it in 5 minutes, I don't think, but I'll try. Most of us tend to like the one or the other better. And that doesn't mean that there's two categories, but we just have preferences. And then I think that, and there's a test for it. It's the Curtin Adaptation Innovation Theory test that you can do, and then you find out which one you are. So you can apply this at your company, because people that like to fix stuff, so maintain or make it better, the stuff that is there, are more like a systems engineer or that type of person, like doing requests and And for somebody like Christian, this is basically the way that he works, or at least unless he's blocked, this is how he's trying to work. Yeah. Right. So I sort of posed to myself the challenge to come up with to understand why is this shitty code? Why is this not good code? How can I sort of make it readable? How can I reuse the functions? Although it's a very small sample, I understand. And how can I make it more descriptive? Yeah. So I looked at the array and I didn't know this before. I'm not so much into JavaScript. There's a map. There's a join. There's a find. There's a filter. Basically all I need. Yeah. And array is a list. Obviously, it's a list of things. And so this is Wikipedia JavaScript definition. So I had a list and I had first-class functions, higher order functions that I can pass to other functions. So I can do basically all the stuff that was proved 70 years ago with JavaScript. Okay, I put a demo on GitHub. It's going to be on the slides. So if I have, for example, a test list, I can do, oops, forgot this. Oh no, well maybe I can go back. Okay, so I have a test list. I can, for example, do, okay, this is getting too far. Reverse. And I get the same list of integers the other way around. Or I can do a map to a string, so to a different type, right? Very easily, actually. All I have to do is type correctly. For example, this. I'm missing one parenthesis on. Yeah. So it's going to return type B, let's say. If integer is type of A, then type B string, a list of string.
You might want to use X instead of 1.
Where?
Instead of 1, but yeah.
Oh, that's right. I'm sorry, yeah. Okay, we got it. Okay, so just to recap sort of, and now I'm going to go to my example. So first of all, I figured out what it does, and it's actually very simple, and I described it with a test, so believe me that my functional thing is the same as the other one, as the original. So given a string, whatever. Given a list of strings, right, that are elements of a repository URL in SVN or Git, passed to my create application function, I want to filter out the undefined stuff, basically, that is not there. So when the field is empty, then don't display. This is, by the way, the better type of BDD. And when the field contains a slash, I want to replace it with an underscore. And otherwise, I just wanted to put them together with a dot. That's the last one. Combine them with a dot. And those are my tests for it. So I go back. They're still passing. And this is with the original now. It's here. I switch to functional, which is basically just the same function, but done by me. And tests are still passing, so it's the same. This is the original that you saw already. And this is my solution, where first I started by noticing that this undefined stuff is all over the program, actually. So I created an empty and non-empty, which was just an invert of the empty. Then I did a remove slashes. Well, I didn't do it in this order, but this is what came out. Remove slashes function, which is just a function that removes the slashes from a string. And the map numbers, I guess maybe I will. It was just for me to show you guys that I can change it quickly. So, and this is how I refactored it. I created an array with all of the elements. Then I filtered out the non-empty stuff, so threw it out of the array. Mapped it with the remove flashes. So this is already an improvement because I'm actually doing it for each of the elements, where he had it only for one element. And I guess this is something that we want in all of them, probably. If it's true for one, then I'm sure it's true for the other ones. And then I join, which is like a reduce, more or less, in mathematical terms, with dot. So I get my thing. And if I want to fuck this up, then all I have to do is say reverse. And my test will fail because it's reversed. But it's very easy for me to change this stuff around, yeah? All I have to do is add a function. Or I could, for example, I could then also map with my map numbers. So let's say that I want to expand the functionality and I want to not allow a number 1 in the name. So this is all I have to do is add a function and execute, and it will fail again because now foo1 is a 1, written 1, instead of a number. Okay, is this okay? Can I move on from the example? Okay, now you've been through the hard stuff, and I'm almost finished, so I might even make it actually. So the downsides of my approach were that, of course, each function operates on every element, yeah. And if you have a huge array like the previous talk, I mean, it's just you kind of sacrifice memory for CPU. You don't have to instantiate objects and stuff, but you have to evaluate on everything in the array. The other thing that I found is that JavaScript out of the box doesn't have lazy evaluation and functional composition, which are in almost all of the functional languages. So maybe with element stuff, this will be there. But it's not there out of the box, and it's actually possible. It's actually possible to do. So this is an example on how to do functional composition. And just to show you, this is really good. This was his conclusion at the end of, he basically built a functional composition, and then he said that to mathematicians, functional composition is a very simple concept, but basically in coding it doesn't quite work always, right? And yeah, coding is not mathematics, so it's not a silver bullet or anything like that. But I think that the good stuff, sort of, that I achieved by this can be simply described by this picture. This is Rich Hickey, the creator of Clojure, and he talks about how you can simplify and complex your program. And basically, an intertwined program where the functions, or actually the functionality is really inside of each other, is very complex, hard to understand, and hard to talk about, especially. And of course, you're not going to achieve this, but you kind of want to tilt it that way as much as you can, because it becomes easier to talk about. You can reuse functions or reuse code in your other applications and stuff like that. And I will end by calling this presentation thoroughly incomplete. Those were the words actually that Kurt Gödel used for the solution that Alonzo Church proposed. So I added all the links and stuff, and you can just go there and read more if you like. But that's it.
Thank you for watching this talk. Down below, you can find our channel, ViennaJS, where you can find a lot of different videos about front-end and back-end JavaScript. And feel free to subscribe.